When we were learning about delta G and Gibbs free energy in Unit 5, we had said that when delta G is a negative value, we know that it is thermodynamically favorable in the forward direction, and when delta G is positive, it's not thermodynamically favorable. Okay, cell potential tells us the exact same thing. Okay, there's a relationship mathematically between delta G and the cell potential, which is this value right here, or this equation right here, okay, where delta G standard is equal to negative NFE. And this one they will make you do the math on, unlike the previous equation that we looked at, okay? So this, again, this N here, we talked about that in a previous video, is the number of moles that are transferred in that reaction. So you need to be able to look at the two half reactions and figure out how many electrons all total are being lost, how many electrons are being gained, okay? So N is the number of moles of electrons that are transferred, okay? And then this capital F, which again we also saw in the previous equation, is what we call Faraday's constant. It is 96,485. That is on the equation sheet if you need that. And that is measured in joules over volts and over moles, okay? Now, delta G is typically measured in kilojoules, so usually when you use F, you're going to use it as 96.485, and then it's kilojoules over volts moles, okay? So again, that equation, delta G equals negative NFE, that's given on the equation sheet, so's Faraday's constant. And again, then it's written as 96. I'm looking at it right now. It's written as 96,485. But on there, it does say coulombs per mole. And coulombs is something we are going to talk about here in one of these next few videos. Okay, but they also tell you that a volt is equal to a joule over a coulomb. Basically, it's a joule over volt mole. That's what you need to know. Okay, and we'll get to that. We'll get to coulombs here in just a little bit in a future video. Okay. So you replace coulombs in that equation, you get joules over volts mole. So here's an example of this. Use the standard reduction potential table. So again, going back to that standard potential table that they give us at the beginning of the problem, to calculate the standard free energy change, delta G, for this following reaction. So what we need to do is we need to figure out a few things. First of all, we need to figure out the cell potential, and that's what we're going to use the free energy change for. To find. And then we also need to figure out how many electrons are being transferred. So when we separate this into half reactions, we're going to get, this is one of our half reactions, and then we're going to have O2 becoming H2O as our other half reaction. So the top one's fine. We don't need to do anything to that top equation other than we need to put one electron on this side, but there's no oxygens, there's no hydrogens, nothing. Okay, for our second equation, we need to put a 2 here, and then we're going to need to put 4 H pluses on this side, and then we need 4 electrons on this side. And now to balance out the electrons, we're going to put a 4, a 4, and a 4. We're going to multiply everything by 4. And what does that tell you? See how this one loses 4, this one gains 4. That means that for this reaction, N equals 4. So to know how many electrons are transferred, you've got to be able to look at the two half reactions and figure out how many electrons are being lost and how many electrons are being gained. Okay, so now we need to go find our two equations up in the standard reduction potential table. And so one of them, remember, this one's written here as an oxidation. Up there, we're going to find it as a reduction. Okay, so back at our standard reduction potential table here, I've already put these rectangles around the two reactions. So remember, they're both written as reductions, but the silver was the one that was being oxidized. So remember, to calculate the cell potential, it is cathode minus anode or reduction minus oxidation. So the cell potential for this reaction is going to be 1.23 minus 0.80. And remember, even though this is a 4. Remember, we had to multiply those by 4. Remember, that does not affect the cell potential. So it's just 1.23 minus 0.80. So the cell potential is 1.23 minus 0.80, which is 0.43 volts. So we've got our cell potential now. We've got our number of electrons that are transferred, which again was 4, if I remember correctly. And so now we can go ahead and figure out the delta G value. So delta G is going to equal negative, the number of electrons that were transferred are 4, times Faraday's constant, 96.485 kilojoules over volts moles. And then we've got our cell potential, which is a positive 0.43 volts. So notice again that since it's delta G equals negative NFE, that if the cell potential is positive, this number is always positive, this number is always positive. So if your cell potential is positive, then delta G is going to be negative every single time. Okay, so negative 4 times 96.485 times 0.43 volts gives us a delta G value of, let's see, it didn't really give us any room here. So delta G, our final delta G value equals negative, I would round that to negative 166 kilojoules per mole. Okay, and that's how you use that equation, is you find the number of electrons that transfer. Faraday's constant's always the same, but then you do need to know the cell potential as well. So the relationship between these three, between the equilibrium constant, cell potential, and delta G is the following. Okay, if it is thermodynamically favorable, again, don't use that word spontaneous, use thermodynamically favorable. If it is a thermodynamically favorable reaction, we know that delta G must be negative. We know that the equilibrium constant is greater than 1, and now we also know that the cell potential must be a positive value. Okay, and then the opposite is also true. If it's not thermodynamically favorable, then delta G is a positive value, KEQ is less than 1, and the cell potential is going to be a negative value. Okay, remember, for all voltaic or galvanic cells, this is true. Okay, for all electrolytic cells, which we're going to talk about in our next video, so these ones here, either voltaic, again, sometimes they use the word galvanic, and then down here, these ones are the electrolytic cells. And remember, all of these cells are called electrochemical cells. Don't confuse electrochemical with electrolytic. Okay, those are different. Electrochemical is just every kind of cell. It's voltaic, galvanic, or electrolytic. Okay, within the electrochemical cells, there are the voltaic galvanic cells, which the cell potential is always positive on, and then there's the electrolytic cells where the cell potential is always negative, and then our delta G value is positive and KEQ is less than 1. And then when you're at equilibrium, and that's tough to say because some of these, even when K is greater than 1 or less than 1, you're still at equilibrium. But more importantly, when delta G is 0, then the cell potential is also 0 and vice versa. Okay, and so that's how your relationship between delta G and the cell potential.